Hey gentlemen, I wanted to start by doing a little derivation for you and then talk about how we can use equations in problems. It was kind of vague. Well, anyway, we start with this definition of potential as UE over Q. But then I can say, okay, if that's what V is, then delta potential energy over Q equals change in potential. Okay. Now this is called alternately change in potential or potential difference or voltage drop, or, and this is confusing, voltage. Right, so when we say a battery has a voltage of 1.5 volts, we really mean there's a 1.5 volt drop from positive to negative. Okay, delta UE, change in potential energy. Well, remember, change in potential energy is equal to the opposite of change in kinetic energy. Right, whatever loss of potential is a gain in kinetic. Okay, and also delta K, change in kinetic energy, or the net change in kinetic energy, is equal to the net work. So I can use these to rewrite this as net work over Q equals delta V. Well, remember that work is force times displacement, assuming that the force and displacement are going in the same direction. Sorry, it's negative W net over Q is negative F delta D, assuming force and displacement go in the same direction, over Q equals delta V. All right? Now here's another thing I can do. If force is constant, right, over the displacement, if it's not changing when you displace the charge, then F divided by Q, well, that's just field. Okay? Negative E delta D is delta V. Okay. Well, here's what that means. I can kind of rewrite this in a different way. I can write it as delta D equals E equals negative delta V over delta D. Here is where that's kind of cool. Remember Kieran called out today, as he's wont to do, that if you have a contour map like this, it's steeper over here. Well, remember, each of these is a particular V. 1, V2, V3, V4, etc. So it's steeper on this side, to me use the analogy, because to go from V4 to V3, I have a much smaller delta D, right? So here, the delta D is really big. And here, the delta D is really small. What's that going to do to this equation? It's going to make the numerator the same, right? It's the same delta V to go from here to here as to go from here to here. But the delta D is much smaller on this side, so that's going to make the field bigger. Okay? So this equation says in kind of energy terms, the steeper the slope, the delta V, the bigger E. Okay? And that's going to be useful, I'll tell you, in a problem like number 10. Sorry, actually, this might be a different one for you, where you have these equipotential lines, and you have to figure out which way the field goes. Remember what I said in class, that the field points perpendicular to the equipotential lines. So like over here at point T, the field would point this way, right? Okay, over at R, it would point this way, etc., etc., etc. Note that this only works for a constant field. If the field's being created, though, by a charge, like a positive charge over here creating this field's not constant. As you go farther away, the field weakens. So this equation here is pretty useless. So let's use this equation only when the field's created by witches. By which I really mean, of course, only when you don't really know the cause of the field and don't really care about it. Okay. In the next video, I want to talk to you about this equation, which is useful for finding potential. Note, this is actually a V, it's not a delta V, when the field is due to a point charge. See you in a little bit.